Hello, I'm back to actually plug in the numbers on this set 13 problem 2. Okay, I want to do this partly because the units are kind of freaky, and the main upshot is just don't worry about the units, they all take care of themselves. Okay, so remember last time I introduced this idea, we have this LRC circuit. Q is the charge on the capacitor, and I is the current going through the rest of it, which is just the derivative of the charge on the capacitor. Okay, so we have an initial condition that the charge on the capacitor is initially 6 times 10 to the minus 9 coulombs, or 6 nanocoulombs. That's coulombs, and that's capacitance. And there's no initial current. I is dq dt, or q prime of t. So that's coulombs and that's amps that in this problem. And then the units of inductance, or L, are henries. But 1 henry is a big inductor. So L in our circuit is 120 times 10 to the minus 6 henries. Or if you went to an electronics store, you'd say that's 120 microhenries. This is named after Joseph Henry, an American physicist with those dates, born soon after the American Revolution. The capacitance is 100 times 10 to the minus 12 farads, or 100 picofarads. And that's named after Michael Faraday, a British, actually an English physicist who's very famous, who lived about the same time. All right, so we have the differential equation, and we plug in Q is e to the RT, we get the characteristic equation. And I want to point out that I had an error in the last video. I wrote R over C here. I should have written 1 over C that comes from that term. Plugging in e to the R2, e to the RT for Q, just give 1 over C, e to the RT. I factored out the e to the RT to get that. Okay, and I also did, I kind of started one when we have R equals 0. So when this guy's undamped, by the way, when this is undamped, the charge is it's going to go oscillating back and forth from the top plate on the capacitor to the bottom plate, and because there's no resistance, it just keeps oscillating forever. And we'll see that from the math. We had R is plus or minus I omega naught, where omega naught is 1 over LC. Okay, and if I plug in these on the calculator, I don't think I'll take the time. I plug in those numbers on the calculator, and I have it here. I get 9.129 times 10 to the 6. And that's going to be radians per second. And radians is unitless. You could call it inverse seconds. All right. And so basically, we know that Q of 0 is that. So we can kind of solve this by inspection. Q of t is the initial charge, 6 times 10 to the minus 9, times cosine of, I can't type in omega naught in WebWorks, so I'll just write it out. 9.129 times 10 to the 6 t, and that's all coulombs. So that's the answer, and then this is the part you'd actually type in to WebWork, okay, because the coulombs is outside of that. Cool, and that's really fast, right? That's a huge number. In fact, the period is 2 pi over omega naught. Turns out to be 6.883 times 10 to the minus 7 seconds. S is the official abbreviation for seconds. I sometimes like to put SEC because it's clear what I mean, but I'll use the official. That's the period. So might actually want to mention that the frequency, this is not asked for, but the frequency, which is 1 over t, is 1.5, no, 1.45, 3 times 10 to the 6 cycles per second. Cycles is unitless, second to the minus 1. A cycle per second is called a hertz, Hz. Not that you hurt yourself, but it's a guy's name. This is also usually called 1.453 million hertz or megahertz. You probably heard megahertz, like on radio stations and stuff. So that's really fast. As I mentioned last time, this thing, the way that this oscillates so fast is what makes our high-speed world work. But they don't really ask for that, so I've circled what they asked for. So let's now come to the critically damped. R is, I'll call it R critical. And actually, I'm going to take a little bit of room here. Might need it. All right. So R is R critical. So as I said last time, we get that when this quadratic equation has two equal roots. Let's just use the quadratic formula. R is minus b plus or minus square root of b squared minus 4 times a times c. C is 1 over c. Okay, all over 2a, 2l. Right? So we have repeated roots when the thing inside the square root is 0. So R crit satisfies the equation for R squared minus 4L times 1 over C is 0, or R squared, bringing that over, is 4L over C, or R is equal to square root of 4L over C, which is square root of 2. Sorry, square root of 4 is 2, which is 2 times square root of L over C. That's R crit. All right. Okay. So let's see. You can just plug that into, so for me, plug that into the calculator. We do plug those numbers in. R crit in this case is 2 times, I'll talk about it a little bit, 120 times 10 to the minus 6 over 100 times 10 to the minus 12. Okay. Really didn't do this for omega naught, but the same kind of thing happens. I don't actually put the units in here. I just put in the numbers in front of henries and in front of farads. In fact, I'll get rid of this because for this problem, really, it's the henries and the farads that matter, not the picofarads. Okay, so this is kind of useful. So let's simplify this. This is going to be 2 times square root of 1.2 times 10 to the minus 6 over 10 to the minus 12 is 10 to the minus 6 times 10 to the plus 12, or 10 to the 6. So square root of 10 to the 6 is 10 to the 3. So R crit is equal to 2 times square root of 1.2 times 10 to the 3. So let's see, I'm going to clear that. So R crit is actually equal to, well, whatever it is. You can type that into the into web work as the answer. And by the way, 1,000 with units, this is ohms. That little kind of symbol looks like a horseshoe, stands for ohms. And 1,000 ohms is a kilo ohm. As double O, you spell that K-I-L-O-O-H-N. Okay, there's our crypt. So I don't have to write that again. So this is another webwork answer. Okay, now I can take that R crit, and since that's 0, I can plug it in here and divide by 2L and get an answer. And you'll probably say, whoa, I've seen that number before. And let's see how that goes. Actually, it turns out that the fact that when R1 equals R2 equals minus omega naught, that same number, omega naught, when R equals R crit. Wow. Actually, let me just do a little bit of that's kind of an amazing fact. Let me do a little bit of why it happens. I take this equation, I get R squared plus R over LR plus 1 over LC is 0, right? I'm divided through by L. Now, when R is R crit, this is actually the form R plus something squared equals 0, right? So at the correct value of R, this is just a perfect square. That's what it means by a repeated root. And what's that? So I get the first term in the FOIL. First term is R squared. The O and the I combine in some way that we don't worry about, because the last term squared is 1 over LC. This has got to be 1 over LC inside the square root. This is the only thing I can put here to get the R squared term and the right constant term. So in fact, R1 is R2 is equal to minus 1 over LC, right? Which is, remember, that's minus omega naught. Cool. Yeah, so remember the roots, so that the roots we have in the first part are plus or minus I omega naught. Two different roots, but they're complex. The roots we have in the second part are omega naught, negative omega naught, and repeated negative omega naught. So now let's think about the solution. Where's my eraser? Here it is. We have that, we want those initial conditions. And all I really need is the roots. So I can get rid of all this, give myself some room. So the general solution, that critical damping is Q is C1 e to the minus omega naught t plus C2 t e to the minus omega naught t. And as I've done before, it's kind of nice to factor out the e to the minus omega naught t. So that's Q prime is going to be the first derivative of the first, C2 times the second, plus the first times the derivative of the second, which is minus omega naught. That's a factor of minus omega naught, times e to the minus omega naught t. Right? Cool. So to find the C1 and C2, I plug in the two initial conditions, and I have Q of 0 from the formula is when t is 0, that term goes away. When t is 0, that's 1. Q of 0 is C1. And I set that equal to 6 times 10 to the minus 9. And then the derivative, Q prime at 0, is using this formula. It's going to be C2 times 1 plus C1 plus 0 times negative omega naught times 1. So I'm going to set that equal to 0. Right? So C1 is 6 times 10 minus 9. C2 is bringing that over omega naught times C1. Right? So now I can put those together, and I get Q of t is C1 e to the minus omega naught t, and then plus C2 is omega naught C1 e to the minus omega naught t. I factor out the C1, and I get 1 plus, it's a plus, omega naught t e to the minus omega naught t. Okay, so I have symbols in here, but C1 is known. C1 is our 6 times 10 to the minus 9. Omega naught is known. I think it's been erased now, but I'll rewrite it. So what we actually have to do is put into web work is going to be Q of t is the C1 to 6 times 10 to the minus 9 times 1 plus, and what is omega naught? I have it in my calculator still, 9.129 times 10 to the 6 t. All times e to the minus 9.129 times 10 to the 6 t. And that's going to be coulombs. That's the charge on this capacitor at any time. And so what happens here is that before I open the switch, there's a bunch of charge on the capacitor. When I open the switch, it just schmoozes and evens itself out. The charge will go to 0 very quickly. Here's T, and here's Q. All right. So in fact, I have this thing plotted with the computer. I'll share the screen here with Mathematica. So I've plugged in the omega naught, and I get the 9.129, right, rounded to 4 significant figures. Remember, use 4 significant figures in web work to be safe, times 10 to the 6. And then here's what the undamped oscillator looks like. I just get a cosine that keeps oscillating forever, never decaying, if there's no friction, no resistance. But here there's critical damping, critical resistance, and then the solution just very quickly decays down to 0. And that's, you see this is what I plugged in before. Okay. Right. So I can here we see them both, so we can get a nice shot of both of them. So if there's no resistance, we get like the 6 nanocoulombs that just bounces back and forth between the upper and the lower plate of the capacitor. I've got critical damping. The charge just evens itself out, so there's no charge on the top or the bottom. And there you go. So if you want me to send you this Mathematica notebook, we do have a license on campus for Mathematica, and you might want to learn how to do it. I can send you the notebook. I'm not going to post it because I'm not going to post it, but I'll send it to you personally if you ask me by email. All right, well, good luck on this problem. There's some kind of unfriendly numbers, but like I say, those numbers are what makes all of this possible. The fact that frequency is so high, millions of cycles per second. Wow. Okay, bye.